Hello everyone, I am Dr. Somnath Kar, Assistant Professor from University Department of Physics, Kolhan University, Chaibasa, Jharkhand. Today I am going to discuss a fascinating scientific phenomenon known as beta decay and associated neutrino hypothesis. The intricate topic delves into the depth of subatomic particles and their behavior, which offering a glimpse into the mysterious world of quantum mechanics. So in this lecture, we are going to discuss following items. We start with what is beta decay, what it means, and why the scientists found so much difficulty in explaining it. Then we'll see how the idea of a new particle which was discovered, which was at that time undiscovered experimentally, and then we will discuss discuss how the hypothesis shaped some key principle of physics followed by the properties of it, and we will see the how many types of this new number are in this particle physics. So let's start with a brief story of the discovery of radioactivity and where the beta decay phenomenon stands. Radioactivity was first observed by Henry Becquerel in 1896, and it was a completely accidental observation while he was working on a sample of uranium salt. Then Madame Curie and her husband Pierre Curie also observed the similar phenomenon on radium and polonium. In 1899, Ernest Rutherford finds that there are two types of particles which are emitting, and he named them as alpha and beta particle. And here you can see a schematic diagram of that kind of experiment what was done by Rutherford at that time. And you can see that alpha particles or beta particles coming out depending on their magnetic field they are bending. So soon after, Becquerel measured the mass to charge ratio of the beta particle and identified that it as an electron. So a typical beta decay from a nucleus can be understood from this picture here. So basically there are beta particles and its opposite particles also there, that is the electron, and its opposite particle is positron also, which was discovered later on. So there are different kind of beta decays, and basically the three types of beta decays: beta minus, beta plus, and electron capture. We will see at the end what are these. So now scientists thought from where this electron come from. Are they orbital electron or from inside a nucleus? But from the energy of the emitted beta particle, the idea of the orbital electron was true. We know that the nucleus does not contain any electrons. So the answer is this: these electrons are coming from the nucleus but instantaneously. That is, as they are produced, they come out from the nucleus immediately. The basic process involves is here is the transformation of a neutron into a proton. Basically you can see in this cartoon. So now scientists found themselves in a serious problem because of this beta spectrum you can see here, where the y-axis is the intensity, x-axis is the kinetic energy of the emitted beta particles. So now the energy curve is a continuous curve. Emitted electron any energy between 0 to the maximum attainable energy, which you can see from this curve, but theory suggests a constant maximum energy of for a particle of the beta emission. This is a clear violation of principle of energy conservation. Also beta decay process seems to violate angular and momentum conservation, which we can see from this decay processes. From a neutron to a proton, when an electron is coming out, the neutron is a spin half particle, proton and electron all are spin half particles. So the left side and right side violate the spin conservation. Also we can see there is a apparent violation of linear momentum conservation, because a parent nucleus when it decays into a beta particle, and the daughter particle or daughter nucleus, since it is a two body decay process, it the daughter nucleus and the electron should come out back to back, but in experimental we see that the electron is not always back to the or opposite to the daughter nucleus. So the astonishing outcome of this beta decay puzzled the whole physics community at the beginning of the 20th century. Pauli in 1930 came up with his neutrino hypothesis to shape the principle of conservation of energy and momentum. He hypothesized that there must be another particle accompanied to the emitted electron, and he named them as neutrino. Later on, in 1933, Enrico Fermi built the theory of the beta decay. So, according to the Pauli, the new particle, that is the neutrino, must have the following properties. It must be chargeless. It must have a almost negligible mass. It should be a, spin half particle like electron, that is it is a fermion. It must have small magnetic moment. Also, it must act very weakly while interacting with the other particles. So we will see now the different beta processes. That is, first one is beta minus decay, where a neutron gets converted into a proton. You can see in the picture. Then a beta plus decay, where proton gets converted into a neutron, and an neutrino and a positron comes out. So these are the antiparticle, antineutrino, and this is the neutrino is the that is the particle. Similarly, electron is the particle, positron is the antiparticle. And there is another process, electron capture, where and orbital electron has been captured by a proton, and it converted into a neutron, and a neutrino is coming out. These are the beautiful picture of Feynman diagram, where you can see the quark level structure and weak interaction, where a W boson is weakly interacting here. This is the mediator particle. So this is the beautiful picture, and it depicts and it gives the basic theory of the beta decay. That's all. Thank you for your attention, and I hope you have enjoyed this lecture. Thank you very much.